So if I'm talking about learning formal proofs for circle geometry, when I help students in class, I often find that they feel a bit overwhelmed by all the choices they have to make when proving a proof. So let's just talk about how you will be examined on proofs and what are the various steps. So there will only ever be one proof question in your paper 2, and it will typically be between 5 and 8 marks. All right. So there'll be one proof or formal proof question. Let's call it formal proof. So there'll be one formal proof question, and it will typically be 5 to 7 marks. That's the first thing, because I know students get very worried because they see all these proofs. And the thing you have to remember is, if, for example, you're getting 35 marks on circle geometry and there's only 5 to 7 marks on proofs, you'd be silly to not look at proofs, but you must realize it's only a small part of the circle geometry world. Then within circle geometry, there are 4 main sub-steps. And I find that if students understand these 4 steps in their brains, they almost can keep this idea there to help them. So when you're proving something, you will always be given something to start with. So I call that the given. And you might be given a circle. Normally you're given a circle with center O, and then you're given something else. So it might be that you are given a circle with center O, and you are given a chord AB, and you are given and then with a line to the point C. So that is the stuff that you're given on which you start the proof. Then for the theorem, there's always going to be something that you're required to prove. Now, the required to prove bit is just kind of what you want to end up with. So for example, here, it might be that, over here, they probably would normally say that they give you this whole thing, and they would also say that AC is equal to BC. So this is all the setup information. Then you are required to show something. And in the case of this example that I'm making up, we might show that OC is perpendicular to AB. Another thing that students often find is that they try to memorize letters, but you don't really want to memorize letters so much as, because I might give you OABC, but I can also use DEF. So that is better to understand kind of the relationships and then go from there. Okay, now I want to ask you, from what you remember from class, you're given something to start with in most proofs. You then know that you have to prove something, and normally this is still all given to you. The first time students have to get involved is a construction. Who can tell me what a construction is? Or maybe for this question, what do you think the construction would be? Because this is one of the circle geometry theorems. What is a construction? Because normally this is the first marks that are available to students in a proof. Let me know in the chat or pop your hand up. What is a construction? Aha, Tando and Amukalani, and Morgan says to complete the triangle or the drawing. And people are saying I must connect O to A. Okay, so a construction is just an extra bit on the drawing. Now, in this case, in this particular proof, which I'll show you now, you want to construct OA and OB. And what we normally do to make sure our brains don't get confused is we make sure that the construction is with a dotted line. Okay, so this would be the first marks for students, making sure. So when you learn this, you want to learn what the construction is. Now, once you've done the construction, this is when the actual proof starts. And so there's different ways to do the proof. But before we get going here, what do you think one of the main give me some of the tools that we normally use to help us prove something in this stage. So this is the 4th stage, the actual proof. We want to try and actually prove that OC is perpendicular to AB, but we normally have to use other techniques. What techniques, okay? So we can't, Morgan, with a formal proof, use, in this case, the midpoint theorem. We do use the fact that we know that AC is equal to BC. We use that. We often, in this type of situation, is we have to use something called congruency. And we are going to work with these two triangles to help us prove that OC is perpendicular to AB. Yes, we're also going to use radii to help us as we go. But before, I'm actually going to show you the exact proof. But give me a thumbs up if you guys recognize the word congruency and you know about the different cases of congruency. Okay, so now that I've showed you the 4 steps that are always going to be in proofs, let's go and look at what this full proof looks like with a full drawing, and you guys will be able to follow it through with me. Okay, so here is what this theorem looks like. If we have to look at the formal proof, I'll show you what it looks like in the exam after this too, but let's just have a quick look over here. So you are given something. You're given any circle O and C, which is the midpoint of AB. So you can see it over here. Okay, now what we want to do, what we're required to prove is OC perpendicular to AB. So that's what we want to do. Then construction is we are constructing OC, OA, and OB. So I would prefer if this drawing had these things being dotted lines. But give me a thumbs up if you see how the purple bits are the bits that I've constructed and how it relates to what I was doing earlier. So earlier on, I would have said, like, I draw in these things and I'm trying to make triangles, because if I make my triangles, I can use congruency. So just let me know in the chat and give me a thumbs down if you feel like, what is this man talking about? But here are the triangles. I don't even have to write that step, but yeah. Okay, now, remember what we're trying to do. We're trying to prove that there's a right angle here, but we haven't got there yet. So what we do first is we say the following. We say, okay, AO equals OB. Now, how do we know that AO equals OB? Well, it's because of radii. So that is radii. We also know that OC is common. Okay, so OC is common. AO equals OB, radii. And when we started this, okay, we started with what we were given, that this was equal to that. Now, what case of congruency has 3 sides? What case of congruency has 3 sides? Okay, the question is, Kanyesile has asked, what does it mean that OC is common? OC is common to both triangles. So OC is both in the triangle on the left over here, and OC is also part of the triangle on the right here. So that's what it means it's common. So if you look here, you will notice there's a yellow side in both triangles. There's a green one, which was given to start with, and the blue one's in common. And so we say that triangle AOC is congruent to BOC, and it's going to be side, side, side. Then what we do is we say that C1, in fact, I would probably add another step here. I would say, let me just make this a bit bigger. C1 plus C2 equals 180 degrees, and that's going to be angles on a straight line, right? But you know that these two triangles are congruent, okay? Therefore, or you can say C1 must equal C2 because of the triangle congruency. Therefore, C1 equals C2 equals 90. So that's what they did there. And if these are 90, then you know that OC is perpendicular to that. Now, I'm going to give you a note. I'm going to drop a note with all the proofs in it for you. So let me just take a moment to do that, because I know there's a lot of detail going on. And, oh, wait, okay, let me just quickly put a link to this PDF, because we won't get through everything today. But what I do want to do is I want to make sure that everyone has access to this. And then I'm mainly going to work on the ideas today. And so let me just take a moment to share. Let's have a quick look. Link. Okay, so I've put a link to a PDF that will be helpful. And then I'll just leave this on the screen for the moment. So all the stuff that I'm working on today, you will see it in this PDF that you can look at later. Okay, let's try another one, because the way to get good at this is just to see these ones kind of, you'll see the pattern. So let me show you this one. This one is slightly different, but it's also got the same ideas here. Notice the subtle differences. It says you're given any circle O with OC perpendicular to the chord AB. So this is what you're given. You aren't given any midpoints, you're just given that that is perpendicular to that. Give me a thumbs up if you understand how this is different to the last one. In that what you're given is different. Okay. Now remember, we said there's 4 steps. What are we trying to prove? We're trying to prove this time that AC is equal to BC. So AC is equal to BC. So basically the green is equal to the pink. Now, if you want 1 mark, what do you need to do? You need to make your construction. Your construction is to just draw in OA and OB. Why are you making this construction? You're making it so you have triangles. Once you have triangles, what are we going to use? We're going to use congruency. So now let's see how it differs this time. So we know that AO equals OB. Why do we know that? Because they're both radii. We know that OC is common. So let's see if I can see where OC is common. There's OC, it's in common to both. And what else do we know? Well, we know that when we started, C1 equals C2 equals 90. So basically this one over here is equal to this one over here. Now, what case of congruency are we going to use this time to prove that this triangle is equal or is congruent to that triangle? Okay. Now, the case of congruency here, remember, we've got a right angle, we've got a hypotenuse, and we've got a side. So it's not SAS, because SAS would mean we have to have the angle between the two sides, and we don't. The sides that are in common to both of these are the green and the blue, and we don't have the angle between those two. We only have the right angle, the hypotenuse, and another side. So give me a thumbs up if you understand why we must use RHS, or right angle hypotenuse side, when we prove that these two triangles are congruent. Whereas the last time we had to prove that we had to use SSS. Okay, now the last step. Can I please repeat RHS? I can. Okay. If you look at the 3 pieces of information we're given AO is equal to OB. That's the blue bits here. we're given that OC is common, which is the OC is the line in between. So we've got these two sides. But remember, we're comparing triangle AOC and BOC. Now, we don't have the angle between the two known sides, so we can't use SAS. But what we do know is at the beginning, we said there's a right angle down here. So what we've got is we've got a right angle in both, we've got the hypotenuse in both, and we've got another side. And that's why we use right angle hypotenuse side. Now, once we know that this is congruent to this, we then know that this over here must be equal to that over there. So AC must be equal to BC. And what you sometimes see people write is they literally just write the congruency from above, because the congruency is the reason that we can say that. Now, let me give you an example of an exam question of what this looks like, because I know all of you are like, okay, great, but what does it look like in the exam? So let me do that for you. Here's an old exam question that I've pulled, and I want you to try and do this for me by yourself. And then I'll come back and we'll talk about another theorem. But let's just see what it looks like in the old exam. And let me see if I can make it a bit bigger. Here we go. Okay, so I want you to write out what you think your first step would be. Notice how the drawing is looks a little bit different, but I think you should know the steps that we need to do. Yeah, step one is construction. And what do we need to construct? Okay, a triangle, yes. And what lines do we have to construction? So we say construct what? Construct. So construct OR and OS. Notice how they give you all the information. Hey, the given stuff is here, and then the required to prove is already sitting here. RTP required to prove. Okay, now, if we are going to go into the proof stage, what are we going to use to prove these two things here? There's going to be 3 bits of information that I need. Who wants to tell me? So it's going to be congruency. What's the easiest one to put down? Yeah, Mbasa, let's hear from you. What's going to be the first? Can you hear me, Mbasa?
Yes, sir. How are you, sir?
Very good. What's my first step here?
So the first step is OR is equal to OS, and the reason is radii.
Perfect. Yes. And while I've got you, what is another one? Have you got a second one for me, maybe?
OT is equal
Yes.
to OT because it's common. I don't know if that's correct.
Yeah. So we can just say OT is common, or you can say OT is, yeah, equal to OT, common. Perfect. And then what would the last one be? What would be the last bit of information that we would use here?
Oh, no, T1 is equal to T2.
Yep.
Given, I think. I'm not sure, sir.
Yeah. So the important bit is T1 equals T2, but it's 90 degrees. So we know that these are perpendicular. Thank you so much. That was awesome.
Thank you,
and
sir.
Then the last thing we do now is we're just going to say that triangle, and you can start with, I'm going to start with O. So triangle ORT is congruent to triangle, let's say OST. And what is my case of congruency going to be? What is my case of congruency going to be? So I've got a right angle, I've got a hypotenuse, and I've got a side. So we're going to have RHS, and therefore RT, so RT is going to be equal to TS. And the reason is going to be the congruency that we just proved above. So literally the congruent, we just write it down exactly like you just did. And that's it. Now, I know that's still hard. That's why I've given you the proofs things, but give me a thumbs up if you can follow the general logic of what we were trying to do there. Give me a thumbs down if you still feel very lost in the process. Okay, because I want to squeeze in a little something before break. So this is probably the third most common theorem that is tested in exams. I want to go into probably the second most common. So, we're done already. So let's keep going. I'm not going to go over this one over here. This isn't tested very often. It is technically on the list, but it's not that tested that often. This is the one I want to talk about very quickly. So if we look, this is probably, maybe this is even, yeah, either this or the tan chord is the most commonly tested theorem. What is this theorem about? The one that I'm showing you on the screen now. What is this theorem all about? And look at how it dances around. Any ideas? Okay, so this is called the angle at the center is twice the angle of the circumference. But when we go, remember the steps that we're going to follow when we're proving something. We've got the given, we've got the required to prove, we've got the construction, and then we've got the proof. So we're going to use that. But the sneaky thing here is, look at this shape. I call this the arrowhead part. And that's good. But if I keep going, notice that it looks like it's falling over. Now, this theorem has three different figures that you should be sort of familiar with. The arrowhead is most commonly tested, but there's the falling over, where the angle at the side or at the circumference is just, it almost looks a bit like the butterfly, but it's not. And then the third variation is when it's falling over. Notice how the angle at the center is the reflex angle, and it almost looks like it's fallen over. So before I begin looking at the proof for this theorem, can we all give me a thumbs up if you see figure 1, you see, I think this is the one they say is figure 2, and then figure 3. So you're aware of the three different shapes that you get. Okay, let's learn how this theorem works. Let's learn how this theorem works. Okay, so blah, 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 looks so scary and overwhelming. I want you to ignore all the stuff on the screen except for this bit here. So are you happy that you see, give me a thumbs up if you see the three different figures and you see the 4 steps I was talking to you about earlier on. Okay, now, all this theorem does not have any congruency in it. All it uses is the exterior angle of a triangle and radii. So when you are learning this one, all you need to worry about is exterior angle of a triangle and radii. In some ways, this theorem is even easier, but it's important you have the basic ideas. And there is one really important bit called the construction. So let's look at that. So what are you given? You're given any circle O, now that's not exciting, with a central angle BOC. Now the central angle BOC is just the angle at the center, and an inscribed angle BAC. So you've got that. And both subtended by the arc BDC. So that's this thing here. What's different, though, is that the angle at the center and that the angle at the circumference do look a little bit different depending on what drawing you are in. So let's just see angle at this. Sorry, it's not the most subtle. but can you see the slight differences about the angle at the center and the angle at the circumference? Okay, so that was me trying to make it clear. Now, what do you need to prove? You need to prove that the angle at the center, BOC, is twice the size of the angle at the circumference. But what you notice, okay, so that's that. So what is the thing you actually have to learn? You have to learn to join AO and produce it to E. So all that you need to do is, when you've got your arrowhead, or you've got this, you just need a dotted line that goes from the circumference to the center and then goes a little bit further. That is it. If you look at the other figures, even though they look different, you just need to make a construction, and here you need to make a construction as well. So that's your first bit of learning work. Give me a thumbs up if you know how to make the construction. All right. Now, even though this textbook does a lovely job of showing stuff, I still think it's a little bit more confusing than it needs to be. So all I'm going to do is show you the logic behind this proof, and you can use, as long as you're consistent, your labeling will be fine. So they've said A1 is equal to B. I'm just going to keep it really, really simple. I'm going to say, let this angle over here be X. Let me see if I can zoom in a little bit. Okay. I'm going to say, let this angle over here, so I'll say let A1 equal X. What is the size of angle B going to be? If I know A1 is equal to X, what is the size of angle B going to be? And then we'll take a break in a moment. So B is going to be X, and the reason is radii. Okay, awesome. Now, let me say that I say that A2 is Y. What is angle C going to be? We're going to, as soon as we finish this, I'll take a break. Angle C is going to be Y, and it's going to be the same reason. It's going to be radii. Okay, now, what is the size of E1 going to be? So what is the size of E1 going to be using this drawing here? Look at its relationship. Remember, I told you, what's the other big idea in this proof? It's exterior angle of the triangle. This E1 is going to be made up of these two over here. And so we'd say that that is 2x. And then what is the size of E2 going to be? It's just going to be 2y. And the same reason, exterior angle of a triangle. Now, sorry, I'm running out of space, but I'm just trying to show you this as simply as I can. All right. Well, actually, let me just stop for a second. Has everybody followed? Give me a thumbs up if you understand why the two reds make a blue, the two greens make the black. Okay. Now, all that we have to do now is say that triangle, and I would suggest looking at the notes, but all we can say is angle BAC is equal to X plus Y. And we can say angle BOC is equal to 2X plus 2Y. So if you look at this was an X, this was a Y. This was a 2X, this was a 2Y. So the angle at the center is 2X plus 2Y. The angle at the circumference is X plus Y. Okay, I'm losing some of you here. We're going to take a break in a moment, but all I wanted to show you is basically the proof is now done. So let me go look at the neater writings. You guys can all see this. So all we did here was we said that we made the two things equal, like AO equals OB radius. Then we knew that that one plus that one is equal to that. And we showed that the angle at the center is twice the size of the angle at the circumference. So that's all we had to do in terms of that theorem. Okay. Now, because of time, I'm not going to go through everything, but you could get 4 marks by just even, in fact, oh, you know what? When we come back after the break, we're going to give this one a go. Here's a past exam question, which you can have a look at, and we'll do it together afterwards. So if you look at that question, if you're feeling stressed, don't worry. We're going to look at this exam question when you come back. We just need to take a quick break. Okay, so I want everybody, turn your cameras on, stand up with me, because I fear that I may be stressing some of you out a little bit, and we need to take a break. Okay, on your feet, and let's stand up and breathe. One more breath. Yeah, then let's just do some quick small circles and then going into big circles. And then change direction with big circles and go into small circles. Let's just do some rotation. Okay, then shake out your arms, shake out your legs, and then let's just go straight to 20 air skips. And then we're just going to have a short break today. Five more. And just a short break today because we're trying to fit in a lot of stuff. So here is a past exam paper question of the theorem that I just did with you. I want everyone to try and do 10.1.1 using what I was talking about before the break. See if you can get those 3 marks in the bag. And feel free to put your answer in the chat. Okay, let's look at the chat. Okay, so what is O1 in terms of X? Now notice how they've given this over here. Well, we have to say that angle C1 is equal to X. So if we've got that one, C1 is equal to X, and why is it equal to X? It's going to be radii. And then we can say O1 is equal to 2X, and that's because of exterior angle of triangle. And so that's 3 marks in the bag. Now, what you notice is what's quite nice about this exam question is, can you see they actually did the construction for you? You've already got the construction done for you. Now, we haven't done yet. So what I want you to do is I want you to try, it says here, here's the to prove part. It says, prove the theorem that states the angle subtended by an arc at the center is twice the angle subtended by the same arc at the circumference. That's just a long way of saying, prove that this one over here is double the size of this one up here. I want you to try and do that next part for me. What do you think my next thing is going to be? I'll give you some time. You do it and then you let me know in the chat. And then we'll move on to another theorem. I think this Y deserves some attention. You don't have to do all this extra writing, but and that's it. Give me a thumbs up if that felt a bit better than before the break. Give me a thumbs down if you feel a bit lost still. Now, what you're going to have to do in your own time, everyone, is have a look at the different variations. For the most common variation is the arrowhead. Okay, and for those who didn't, I have put a bunch of notes on proofs that you can have a look at. And so I don't want you to be too stressed, but for what I'm going to do now is I'm going to move on to the last theorem I'm going to cover with you today. Okay, and this one, the angle at the center, and then the tan chord are the most popular theorems to assess. So I'm not going to do this one right now. I'm not going to do that one. I'm going to do this, not that one. I'm going to do this one. Okay. So sometimes they call this the windsurfer theorem, and it's often assessed, and I'll show you this, and then we'll look at a past exam paper question. So let's look at the steps. What are we given? Well, we're given a tangent DE and a circle with center O, and then we're given some points on the circle. Okay, the points on the circle are O, A, B, and C. So Oratile, what I would say is also re-watch this exam afterwards. I mean, this thing afterwards. So we're given this. What are we trying to prove? We're trying to prove eventually that A1 is equal to this one over here, which is angle B. So while we're starting this new theorem, give me a thumbs up if you understand that we're trying to prove the pink one equal to the blue one. You recognize that tan chord theorem there. Okay, so you know what part you're playing in here. So how does this theorem work? Okay, well, the thing that you need to memorize is you need to memorize the construction. The construction is the key that unlocks everything. In the exams, most of the time, they're going to give you the given, they're going to give you the proof. You just need to know where to look. But the construction you have to memorize. So what are we constructing? Well, we are constructing a diameter And then once we got the diameter, we get to the other side, we have to connect that to a point on the circle. And what it actually makes, when I think about this one, I think about constructing the diameter and then completing the butterfly. Because you need a butterfly, you need to use the butterfly theorem in this particular proof. And so I complete my butterfly. Now, that is the construction that you need to do. Help the butterfly spread its wings. Now, how does the proof work? Now, there's no congruency in this one, but it does use a couple of different theorems. The one theorem it uses is the tan radius. The other theorem it uses is angles in semicircle. And then sum of angles in triangle. And then it also uses angles in same segment. So those are, it uses quite a lot of theorems to help it prove this one. So what is step one? Let's go. A1 plus A2 is 90 by the tan radius theorem. So that's going to be, let me even draw it in with a bit of a, like these two together. That is going to be 90. Then using the construction that you've done, you know that FCA is 90. So that is going to be these two over here. Give me a thumbs up if you recognize where I got my 90s from, and you're okay with that. Okay, so you've got your 90s that are here. Now what we're going to do, the next step, we're going to talk about this angle F over here. Okay. And we're also going to talk about, let's have a look, A1. Okay. We're going to talk about this angle down here, FCA 90, and then F is 90 minus A2. Okay. If you look down here, you have this little angle called A2. If I want to write F, the black dot, can you see that F can be written as 90 minus A2, which is the little green one down here? So basically this black dot is basically 180 minus 90 minus A2 is that angle. And then A1 will also be 90 minus A2, because you can see, so A1 of it will be 90 minus A2 as well. Give me a thumbs up if you recognize why both the black dot here is 90 minus A2 and this one over here is 90 minus A2. Okay, I'm losing you. Okay, no problem. Let me slow down. If you look at A1, can you see A1 would just be the blue right angle minus the yellow, I mean the green thing here. So 90 minus the A2 is A1. Then F is got 90 in the triangle. There's A2 sitting, the green, and we go 180 minus 90 minus A2, and we get those two bits there. Now, once we've done that, we know that A1 is equal to F. We know that this black dot over here is equal to that dot over there. Okay, but we also know the final step. This is the butterfly theorem. So we know that this one over here, F, is equal to B. And why is F equal to B? It's angles in the same segment. Okay? But therefore, because we know this is equal to this and this is equal to that, we know that A1 is equal to B. And then we've proved the butterfly theorem. Not the butterfly theorem, the tan chord theorem. Now, what I want you to do is I want to do a past exam paper question on this. Could you say that A1 is equal to F because of the tan chord theorem? Buchle, you cannot use the tan chord theorem when you are proving the tan chord theorem. So you can only use the other theorem that you are not trying to prove at this time. So you may not use the tan chord theorem when you are formally proving the tan chord. Okay, it's a good question, Buchli. You may not do that. Okay, there's about 5 minutes left. Let's see what an exam question looks like. I want you guys to try and prove this theorem. And I want you to think about what is the first step that you need to do. What's step one? Here's a 5-mark exam question. And even if you can't get the whole thing right, doesn't mean you shouldn't get 3 out of 5 or 4 out of 5. Don't give up. So what is my first step? I'm leaving out the given. They gave me the given. I'm leaving out to prove. They've done that. I think my first step is what construction do I need to do? Now, I need to actually draw the diameter, don't I? And to get a diameter, I need another point. So I'm going to say construct diameter, and let's call it FH. So construct diameter FH. And then what else do I need to do? So construct diameter FH, but something else I have to do still. That's not enough. Complete the butterfly. What would that be? I would say connect what? Connect H or connect HE. Yes. All right. Now, remember that this goes through the center. What is my first step going to be? We can also say, yes, we can also say label. Let's say, what shall we label? We'll label F1 and F2. So F1 and F2 over here to make life a bit easier. So we know, what do we know? We know that HFG is equal to 90 by tan perpendicular radius. What is the other one that I need to know? What's the other way of making 90? So HFG is 90. We also know that HEF is 90. Why? Why is HEF going to be 90? I think that's going to be angles in semicircle. Now, what did we do next? From what I remember, we worked out what this angle H is at the top. And we said that angle H is equal to 90 minus F2. So that this one over here is 90 minus F2. And that is going to be sum. So H is 90 minus F2, sum of angles in a triangle. And then I also think that angle F1, let's call it, let's say, angle F1, which is down here, or EFG, is equal to 90 minus F2. So we'll make that. Therefore, we can say, and let's use the full name. Instead of using F1, maybe I should call it, what did they use in the question? They used EFG. So we'll call it EFG. And therefore, we can say that angle H is equal to angle EFG. What is my next step going to be? So I've showed that this one over here is equal to this one up here. What's my next step going to be? What's the thing that connects everything together? What does the angle H also have to be equal to? F2 is this little bit down here. So I broke this up into F1 and F2 over here. Let me get that. So I call that one F1 and that F2 just to make life a little bit easier. Okay, so we say H is equal to D, or we could also say, instead of saying D, we can say, what do they use? EDF. So we can call it EDF. And that would be angles in same segment. And therefore, we know what we were trying to prove at the beginning. Let me have a look here. Let me just finish off now. Then we know, because that's equal to that, so we know, therefore, EFG is equal to EDF. And the reason is that you've got these three things that are equal to each other that you proved along the way. So that one is equal to that one, and that one's equal to that one. Okay, we've run out of a bit of time there. And again, I've got a little bit messy at the end, but if you look at the notes, that will help you. Here, can we just put the poll out? I know this is a bit of a tough lesson, and I don't want you to be discouraged because you're only going to get one question like this in your exam.